Hello everyone, good morning. I'm Maya Joy B. Ulao, your science instructor. For today's video, I'm going to share to you the introduction to organic chemistry and its structure and bonding. Okay, let's define first what is organic chemistry. Organic chemistry is a branch of chemistry concerned with the study of carbon and its compounds. Introduction to organic chemistry. Historical background of organic chemistry. Organic chemistry is the area of chemistry that involves the study of carbon and its compounds. Carbon is now known to form a seemingly unlimited number of compounds. The uses of organic compounds impact our lives daily in medicine, agriculture, and general life. In Theory of Paris 1923, organic chemistry may have its beginnings with the Big Bang when the components of ammonia, nitrogen, carbon dioxide, and methane combined to form amino acids. An experiment that has been verified in the laboratory Miller 1950. Organic chemicals were used in ancient times by Romans and Egyptians as dyes, medicines, and poisons from natural sources. But the chemical composition of these substances was unknown. Unknown siya. In the 16th century, organic compounds were isolated from nature in the pure state, and analytical methods were developed for determination of elemental composition. Scientists believe that organic chemicals found in nature contained a special, which is the vital force, that directed their natural synthesis, and therefore it would be impossible to accomplish a laboratory synthesis of the chemicals. Fortunately, later in the century, Friedrich Wöhler discovered that urea, a natural component in urine, could be synthesized in the laboratory by heating ammonium cyanate. This discovery meant that the natural vital force was not required to synthesize organic compounds and paved the way for many chemists to synthesize organic compounds. Again, organic chemistry includes living things are made of organic chemicals, proteins that make up hair, DNA controls genetic makeup, foods, medicines, and examine structures to the right. Okay. Origins of organic chemistry. Compounds obtained from plants, animals, hard to isolate and purify. Compounds also decompose more easily. Torben Bergman, 1771, to make distinction between organic and inorganic chemistry. It was thought that organic compounds must contain some vital force because they were from living sources. Because of vital force, it was thought that organic compounds could not be synthesized in a laboratory like inorganic compounds. In 1816, Chevreul showed that not to be the case, he could prepare soap from animal fat, and alkali and glycerol is a product. In 1828, Wöhler showed that it was possible to convert inorganic salt, ammonium cyanate, into organic substance, urea. Okay, organic chemistry is study of carbon compounds. Why is it so special? 90% of more than 30 million chemical compounds contain of carbon. Examination of carbon in periodic chart answers some of these questions. Okay, carbon is group 4A element. It can share 4 valence electrons and form 4 covalent bonds. Okay, as you can see in the periodic table that in group 4A element can share 4 valence electrons and 4 covalent bonds. Let's proceed to atomic structure. Okay, structure of an atom: positively charged nucleus, very dense protons and neutrons. Negatively charged electrons are in a cloud around nucleus. And now let's know about the atomic number and atomic mass. Okay, atomic number Z is the number of protons in the atom's nucleus. The mass number A is the number of protons plus neutrons. All the atoms of a given element have the same atomic number. Isotopes are atoms of the same element that have different numbers of neutrons and therefore mass numbers. The atomic mass, or the atomic weight, of an element is the weight average mass in atomic mass units AMU of an element's naturally occurring isotopes. And now let's proceed to atomic structure orbitals. Quantum mechanics describes electron energies and locations by a wave equation. Okay, the wave function solution of wave equation, each wave function is an orbital. A plot of orbital describes where electrons most likely to be. Electron cloud has no specific boundary, so we show most probable area. Okay, the shapes of atomic orbitals for electrons. 4 different kinds of orbitals for electrons based on those derived for a hydrogen atom. It's denoted S, P, D, and F. When we say S and P orbitals, most important in organic and biological chemistry. The S orbital, spherical nucleus at center. P orbitals, double-shaped nucleus at middle. And the D orbitals, elongated double-shaped nucleus at center. So now let's proceed to orbitals and shells. Okay, the first shell contains 1s orbital. It's denoted 1s. It means holds only 2 electrons. Second shell contains 1s orbital or 2s, and 3p orbitals. 2p has 8 electrons. And the third shell contains an orbital 3s, 3p orbitals, and 5d orbitals, which has 18 electrons. The atomic structure, electron configurations. Ground state electron configuration, the lowest energy arrangement of an atom, leaves orbitals occupied by its electrons. Okay, there are 3 rules. Okay, the first, lowest energy orbitals fill first: 1s, 2s, 2p, 3s, 3p, 4s, and 3d build-up principle. The second, electrons act as if they were spinning around an axis. Electron spin can have only 2 orientations, up and down. Only 2 electrons can occupy an orbital, and they must be of opposite spin to have unique wave equation. And the third rule, if 2 or more empty orbitals of equal energy are available, electrons occupy each with spins parallel until all orbitals have 1 electron. And now let's proceed to the development of chemical bonding theory. Okay, atoms with 1, 2, or 3 valence electrons form 1, 2, or 3 bands. Atoms with 4 or more valence electrons form as many bands as they need electrons to fill the S and P levels of their valence shells to reach a stable octet. Carbon has 4 valence electrons, 2s2, 2p2, forming 4 bands, CH4. Okay, next, nitrogen has 5 valence electrons, 2s2 and 2p3, but forms only 3 bands, which is the NH3. Oxygen has 6 valence electrons, 2s2 and 2p4, but forms 2 bands, which is H2O. Electron dot structures and the line band structures. And now let's proceed to non-bonding electrons. Okay, valence electrons not used in bonding are called non-bonding electrons or lone pair electrons. Nitrogen atom in ammonia NH3 shares 6 valence electrons in 3 covalent bonds, and remaining 2 valence electrons are non-bonding lone pair. Describing chemical bonds, valence band theory. Covalent band forms when two atoms approach each other closely so that a singly occupied orbital on one atom overlaps a singly occupied orbital on the other atom. Two models to describe covalent bonding, which is the valence band theory and molecular orbital theory. Okay, when we say valence band theory, electrons are paired in the overlapping orbitals and are attracted to nuclei of both atoms. H and H bond result from the overlap of two singly occupied hydrogen 1s orbitals. H and H bond is cylindrically symmetrically sigma band. And now let's proceed to bond energy. Distance between nuclei that leads to maximum stability. If too close, they repel because both are positively charged. If too far apart, bonding is weak. Okay, let's proceed to orbitals and the structure of methane. Carbon has 4 valence electrons, 2s2, 2p2. In CH4, all C and H bonds are identical tetrahedral. sp3 hybrid orbitals, s orbital and 3p orbitals combine to form 4 equivalent unsymmetrical tetrahedral orbitals. And now let's move on to the structure of methane. sp3 orbitals on C overlap with 1s orbitals on 4H atoms to form 4 identical CH bonds. Each CH bond has a strength of 439 kJ-mol and a length of 109 pm. Bond angle, each HCH is 109.5 degree, the tetrahedral angle. And now the sp3 orbitals and the structure of ethane. Two cis bond to each other by overlap of an sp3 orbital from each. 3 sp3 orbitals on each C overlap with H1s orbitals to form 6 CH bonds. CH bond strength in ethane 421 kJ-mol. CNC bond is 154 pm long and strength is 377 kJ-mol. All band angles of ethane are tetrahedral. And now let's move on to hybridization of nitrogen and oxygen. Elements other than C can have hybridized orbitals. H and H band angle in ammonia NH3 107.3 degree. C and H band angle is 110.3 degree. NS orbitals hybridize to form 4 sp3 orbitals. One sp3 orbitals is occupied by 2 non-bonding electrons and 3 sp3 orbitals have 1 electron, each forming bonds to H and CH3. Describing chemical bonds, molecular orbital theory. A molecular orbital or MO, where electrons are most likely to be found, specific energy and general shape in a molecule. Additive combination bonding MO is lower in energy. Subtractive combination anti-bonding MO is higher energy. And now let's move on to drawing structures. Drawing every bond in organic molecule can become tedious. Several shorthand methods have been developed to write structures. Condensed structures don't have CH or CC single bands shown. They are understood. In drawing structures, it has 3 general rules. First, Carbon atoms aren't usually shown. Instead, a carbon atom is assumed to be at each intersection of two lines, bands, and at the end of each line. Second, hydrogen atoms bonded to carbon aren't shown. Last, atoms other than carbon and hydrogen. That's it, class. And now let's move to the summary. Organic chemistry, chemistry of carbon compounds, atom, charged nucleus containing positively charged protons and neutrally charged neutrons surrounded by negatively charged electrons. Electronic structure of an atom described by wave equation. Electrons occupy orbitals around the nucleus. Different orbitals have different energy levels and different shapes. S orbitals are spherical, p orbitals are dumbbell shaped. Okay, covalent bonds. Electron pair is shared between atoms. Valence band theory. Electron sharing occurs by overlap of two atomic orbitals. Molecular orbital or MO theory. Bands result from combination of atomic orbitals to give molecular orbitals which belong to the entire molecule. The sigma bands. Circular cross-section and formed by head-on interaction. The pi bands, dumbbell shape from sideways interactions of p orbitals. Carbon uses hybrid orbitals to form bonds in organic molecules in single bands with tetrahedral geometry. Carbon has four sp3 hybrid orbitals. In double bands with a planar geometry, carbon uses three equivalent sp2 hybrid orbitals and one unhybridized p orbital. Carbon uses two equivalent sp hybrid orbitals to form a triple band with a linear geometry with two unhybridized p orbitals. Atoms such as nitrogen and oxygen hybridize to form strong-oriented bands. The nitrogen atom in ammonia and the oxygen atom in water are sp3 hybridized. That's it, class. Thank you for listening. God bless. Bye-bye.
Thanks for watching.